Okay, good. So last time we nearly finished the discussion about the principle of equivalence. Let's just do a quick recap. Today we will finish the discussion. I don't know how long it's going to take, with something that you've actually asked me to do. And that is showing to you that the geodesic equation, in fact, reduces back to the familiar equation of motion in Newtonian gravity. So that's an important piece which you asked for it rightfully, and I told you that I'll show you. So it will be there. And then we'll do something which is more on the mathematical side, actually. Quite heavy math we'll do today. But I'll explain to you why I'm going to do all that. I want to do all that just to give you the full mathematical picture of the things to follow. So we can do the full derivative. It might be confusing, but we'll go through it one by one. But first thing first, so we start by doing a quick recap on the principle of equivalence. So we spoke about the equivalence principle. We spoke about the equivalence principle, the weak equivalence principle. That's the Otvosh's experiment, and then the strong equivalence principle, which states that at every point in arbitrarily gravitational field, it is always possible to choose a locally inertial coordinate system such that the laws of nature takes the same form as in the unaccelerated Cartesian coordinate system. Of course, only locally in a sufficiently small region of space. The strong equivalence principle. Which is again a direct consequence of Otvosh's experiment. And then we discuss gravitational redshift. Excuse me. We discussed gravitational redshift by giving this example of Ayala and Benny on the top and the bottom of a ladder. And then I argued that this is equivalent for assuming that both of them are not in a gravitational field, but flying in a spaceship, which accelerates. And that means that when Ayala sends Benny something, then he receives it at a slightly shorter interval than the interval in which she was sending it to him. That leads to an observed consequence, which is the gravitational redshift when we are watching distant objects which are subject to a strong gravitational field, such as the sun or stars or neutron stars or white dwarfs or any other type of stars which are subject to a strong gravitational field. And then we moved on to the mathematical description of curved space-time. And I said that when we speak about a freely falling particle, right, then in freely falling coordinate system, then the equation of motion for a freely falling particle right, as seen in the inertial frame, this is simply d squared psi alpha over d tau squared is equal to 0. And in any arbitrary gravitational frame or any arbitrary frame, right, then it is d squared or x lambda over d tau squared, which you can simply write as du lambda over d tau, is equal minus gamma lambda mu nu, where gamma is the affine connection right? Dx lambda over d psi alpha d squared psi alpha over dx nu that connects the new coordinate system, which is arbitrary, right? Not necessarily inertial or freely falling, with the old system. What happens here? You're still seeing my screen, right? Yeah, okay, good. And then we are attributing this second term here. Essentially, we'll give it, you know, it's an acceleration term, right? du over d tau, it's acceleration. Essentially, this is going to be due to the gravitational force. Right now, this is simply a mathematical, you know, manipulation. We show that there is a relation between the affine connection and the metric tensor, because the affine connection, we actually proved it, right, is derived from the inverse of the metric tensor and the first derivative of the metric tensor. And that will enable us to give a physical interpretation, right? Because if the affine connection is somehow related to gravitational force, that means that the metric would be related to the gravitational potential. I'm going to show it to you actually in a few minutes' time. So we show that gamma lambda or sigma lambda mu can be is 1/2 g mu sigma, and then sum of first derivative dg mu over dx lambda plus dg lambda mu over dx mu minus dg mu lambda over dx mu. All right, so here I simply switched mu, the roles of mu and lambda, and here I simply switched the role of mu and lambda. Right? Note that nu really here is a dummy index, right? Because it cancels out. It appears once. Oops. It appears once here, right, as the lower index, and once here as an upper index. So we're really summing over it. Right? Let's see. I said this also has another name. This is called the Christoffel symbol. This is called the right hand side. It's called the Christoffel symbol. It is denoted as sigma mu lambda. Then I argued so the geodesic equation, this equation is in fact representing the shortest path in any arbitrary coordinate system. And I did that by using the variational principle. And essentially we wrote down the equation of motion from the Lagrange, Euler-Lagrange equation using the variational principle. So using Euler-Lagrange equation, we showed that the geodesic equation right, this one here, the equation, represents shortest path in terms of minimizing the proper time. It takes an object to travel from point A to point B. And the classical example I gave you, or the one that to my, at least, is the most intuitive one, is the example of an airplane that you know, is subject to fly on the surface of the Earth, right? The shortest path between here and Los Angeles will take you through the center of the Earth. And an airplane cannot do it. So the airplane is forced to travel on the surface of the Earth. And the shortest path will take you close to or above Greenland if you travel from here to Los Angeles, for example. So that's the reason why when you're sitting in an airplane and you're watching the map of the flight, it may seem to you that the airplane is not taking the shortest path, but it really is taking the shortest path. Of course, the origin of the discrepancy is the inability to properly map the surface of the Earth, which is round, to a two-dimensional flat space, right? Euclidean space of the map. So that is really the issue, not that airplanes are taking you around the globe for various purposes. That's pretty much as far as we did last time. So before I proceed to new material, I would like to stop and ask you if you have any questions about that.
Yes, it relates to the question that I sent you in the email. Generally, when it comes to a metric tensor, and that describes to me any kind of space, how can I infer something about the curvature of that space from the metric tensor?
Okay. We will learn it properly in a few weeks' time when we will discuss curvature of spaces. For the time being, you did ask me related to question number 1 in the problem set. And my answer is that you simply have to have a slight insight and do some coordinate transformation there. There is nothing more than that. If you can show that the metric is equivalent to flat, right? So, independent on the coordinates. I mean, again, think, for example, we gave this example of how the metric looks like. I just look at the two-dimensional flat space in cylindrical coordinates, right? But think of how the metric would look like if you're on the surface of a sphere. Actually, I think you're supposed to be doing that as part of your homework, right? There will be a dependence of the components of the metric on the parameters you use to describe the space, right? So r and theta, for example, or only theta if it's two-dimensional sphere. And then indeed the affine connection will give you non-zero components. For flat metric, as you obviously got right, the affine connection will always be 0. So right now, the only thing you need to do is use your intuition and small mathematical manipulation to show that the metric is indeed can be just by some change of coordinates be made flat. In a few weeks' time, we will learn the precise mathematical way of doing that, which is precise, but I would say is somewhat lengthy. You'll see. You'll have to do. There's a calculation. It's an algebraic calculation, but it's somewhat lengthy algebraic calculation. But again, you'll see that you can get it directly from the metric.
Thank you.
Okay, slightly ahead of time right now. More questions?
I just wanted to ask in regards to what you said, that for a flat metric, flat space metric, the affine connection components will be 0. But in the last lecture, we saw the example that you showed. So it was a flat space-time metric, but the affine connection components were not 0.
Correct. You're right. What we will calculate would be the curvature tensor, but it's not there yet. You're right. I was not careful enough. If the metric is flat, you can find a set of coordinates which will be equivalent to Cartesian coordinates, in which the affine connection will be 0. But in generally, even in flat metric, if you choose other coordinates which are not Cartesian, such as polar coordinates, then the components of the affine connection will not all be 0. In that you're right. The thing that will be 0 again is what's called the curvature tensor, but there is some time until we learn that about this tensor. So for the time being, the only thing that you can do with your knowledge is to find a clever, it's quite simple in that question that I asked, a clever transformation from these coordinates to another coordinates which will resemble Cartesian coordinates. Okay, but you're right. It's a very correct point that even in a flat metric, if you choose the coordinate system which are not necessarily the simplest ones, then the affine connection will not give you 0.
Okay, thank you.
All right. Any further questions? Okay, then as I promised you, I want to do now what's called the Newtonian limit, or the technical term is called the weak field approximation. Or the weak field approximation. So what we want is to write down the geodesic equation in the limit, in the Newtonian limit, essentially. And what we would want to get is obviously to retrieve back the Newtonian gravity, because otherwise we might be in trouble. Right? So what I want to show you now is that when we take the right limit, the geodesic equation gives us back the Newtonian gravity. So what do we mean by Newtonian limit? So Newtonian limit right? That means that there are 3 requirements. So the first requirement is that the particle moves slowly. What do I mean by slowly?
In regards to C?
Of course, right? V is much smaller than C, right? The second is that the gravitational field is weak. And what it means is that I can look at it as a small perturbation of the flat space-time. Okay, so small perturbation of flat space-time. And the third is that the field is static, namely it is not changing in time. Right, unchanged in time. So let's see. Moving slowly, right? I wrote it as V much smaller than C. Of course, the way to write it is that dxi over d tau is much smaller than C dt over d tau. Right? So if I look back at the geodesic equation, right? So the geodesic equation, I can write it as d squared x mu over d tau squared, right? Plus gamma mu alpha beta dx alpha over d tau dx beta over d tau is equal to 0, right? This is the geodesic equation. Then since all dxi over d tau, when I is not 0, are much smaller than the dt over d tau, then I can neglect all the terms here, except for the alpha beta equals 0, right? So that means that I can write down d squared x mu over d tau squared plus gamma mu 0, 0 and then to be c dt over d tau squared is equal to 0. Right? Makes sense? There will be other terms, but they're going to be very small. Right? Remember, if you, for any reason, forgot, right, we have here a summation of alpha and beta. But all the other terms are going to be small. Now, we said that the field is static. So the field is static. So point number 3. Static field means that all the time derivatives of g mu nu are 0, right? Which means that the only relevant terms in the Christoffel symbol, right? We can now simplify it, right? So static field means that I can write down gamma mu 0, 0. This is 1/2 g mu lambda, and then d0 g lambda 0 plus d0 g0 lambda minus d lambda g0 0, right, from the definition which we just learned. But we said that all the derivatives get vanished, so we're just left with minus 1/2 g mu lambda d lambda g0 0. Right. Remember that I used the notation d mu g lambda sigma, just d g lambda sigma over d x.
Saf?
Yes.
Why did you use dt over d tau?
Why did I use what?
dt over d tau.
Because the zeroth component of the 4 vector is just c dt, right? x0 is just c times t, right?
Oh, okay.
Can I ask, when you rewrote the geodesic equation, you basically opened up the summation and used the fact that every other spade component except for the except for the 0th one is very, very small, so you neglected it, and so only the first one remained?
Yes.
Okay, thank you.
Precisely. Okay. And so there are some other corrections, but they're small, right? So I can forget about them. Remember, it's a weak field limit. Right? I cannot do it if the field is strong, but okay. So, and then I use the fact that the field is static, the assumption, not the fact. I assume that the static field, so I can get rid of all the terms that all the derivatives with respect to time of g, right? Because they are not important, they're 0. And then the last thing that I need to use is the weakness of the gravitational field. Now, what do I mean by weakness of a gravitational field? Right, that means that I can decompose the metric. So the weakness of the gravitational field means that I can write down the metric g mu nu into a flat metric, so eta mu nu, plus a small perturbation, which is plus h mu nu, where h is much smaller than unity. Okay, now mu and nu, there are 16 terms here, right? There are 16 terms, but it's, so that's why there is this absolute value, right? So each of these terms, or you can think of it as determinant, it doesn't really matter. Each of these terms is much smaller than unity. Right, so that's meaning, this is the meaning of weak field. Now you can think of it, we're working in Cartesian coordinates, right? So eta will just be the minus 1 plus 1 plus 1 plus 1 on the diagonal and zeros otherwise. Okay, from the definition of the inverse of the metric, right? So remember we had G mu nu G nu sigma, it's just delta nu sigma. We can write down that the first order correction, right, of the inverse metric G mu nu is just going to be eta mu nu minus H mu nu. Right, H mu nu is obviously the inverse of the perturbation, right? So H mu nu, just eta, I don't know, nu rho, eta nu sigma, H rho sigma. It's basically like a Taylor expansion, right? When you have 1 plus epsilon, then the inverse will be 1 minus epsilon. Right? Right. And so again, we could use the Minkowski metric to raise and lower indices. Perfectly allowed here. So when I put this all together, right, then I end up that gamma mu 0, 0 is minus 1/2. Since I have a derivative here and a small perturbation that will give me a second order, so I can simply use here the eta mu lambda rather than G. And then the lambda, right? Since eta is just diagonal, I cannot take the derivative. It's going to give me 0 anyway, so it's d lambda of H 0, 0. Yeah? We all good? Okay, the other terms will just be second order terms. So I don't need them. So let's use that. One we can do approximately, if you're more comfortable with that. Let's put it back in the geodesic equation. Right, so this will be the geodesic equation. So we ended up getting, using the geodesic equation. We end up with d squared x mu over d tau squared is 1/2 eta mu lambda d lambda H 0, 0, and then c dt over d tau squared. Now that still doesn't look very much to like the Newtonian limit, but we're actually quite close to that. What you're familiar with from Newtonian mechanics questions. No? So, what is, let's see, if I take the 0th term, right? So if mu is equal to 0, the only non-zero term from here would be lambda equal to 0, right? Because everything else will get to 0 by the eta. And what is d0 H 0, 0?
0.
0, right? Why? Because the metric is stationary. It's not depending on the time. And so what we are left with is that d squared t over d tau squared is equal to 0. Or dt over d tau is constant. Right? Which again makes sense, right? In the weak field, we're traveling much faster than the speed of light, so our time coordinate is equal to the proper time. Right? So that's what it gives us. What about the spatial coordinates? So the space-like coordinates, right? The space-like coordinates of eta nu nu or ij. These are just the diagonal matrix, 3 by 3 identity matrix. So this is the temporal component. So time the space like component. So we have d squared xi over d tau squared is 1/2. Eta mu nu is just going to give me the identity. So we just have c dt over d tau squared times di h00. Okay, so I divide by 1 over c dt over d tau squared, right? Which is just converting the derivative on the left-hand side from d tau to dt. So we have d squared xi over c squared dt squared equals 1/2 di h00. I'm just taking the derivative of the 0,0 term of the small perturbation of the metric, right, from the Minkowski. Right? So the next thing is to simply identify this 0,0 term of the perturbation H with the potential, with the Newtonian potential. So if we write down, we identify H00 to be minus 2 phi over c squared, sorry, right? That will automatically give us d squared xi over dt squared is minus di phi, right? Phi is minus gm over r, right? It's the Newtonian potential. Right? And that is the Newtonian equation of motion. So that means that we eventually wrote down G00 to be minus 1 plus 2 phi over c squared. Right, so if we do that, it means that the curvature of the space-time is indeed sufficient to describe the gravity in the Newtonian limit, right? If we write it like that, then we retrieve back the Newtonian equation of motion. Again, only in this limit. What I did here is very, very limited, right? Is restricted to the, the conditions that I stated here. Slowly moving with gravitational field and static field. Okay. Cool, isn't it? I'm not cheating, right? We will generalize that, of course, but have this in mind that we're going to retrieve back the Newtonian formula as always if we just take the right limits and we understand what we do in terms of the math. Questions? Yeah.
How did you identify H00 as the potential?
What do you mean, hi? I said it. I said, okay, if I do that, then I retrieve back the equation of motion familiar from Newtonian physics.
Oh, so it's an assumption.
It's a clever guess.
Okay. But
yeah, it's a guess essentially. But of course, this is our motivation, right? When we develop this whole theory, that's a physical motivation, right? Essentially, the theory should be, we said it, the theory should be consistent with Newtonian in the correct limit. We'll say that, you know, of course, it generalizes it, and in other limits, we're going to get different results, of course. Essentially, we'll get to black holes, but right now we're in the Newtonian limit. Okay. Any more questions or comments or concerns of any kind? No? Okay, so we're moving to a different subject now. So you already got your problem set, number 3, which you're supposed to handle by this weekend, basically, I think, or maybe next Sunday or so. Again, if you run into troubles, then let me know in advance, and you know, don't come after and say, oh, you know, I'm late, but can it still be okay? Tell me in advance if you run into any trouble, and as you've seen, some of you, when you ask me questions, I tend to answer them. If you did not get or did not like or did not understand one of my answers, you can ask again, feel free. That's what I'm here for. All right, so the next subject, we're going to do some heavy math now. I'll try to, I always have this problem, you know, I can skip it, but then it will be hand waving on the one hand. On the other hand, it can get really, really confusing. I know it, because sometimes I tend to get confused myself by all the stuff that is there. So definitely, if it's the first time you're seeing that, no wonder it will be confusing. So
Asaf,
yeah,
there's a buzzing, very loud buzzing noise that's really making us hard to hear. It gives us a hard time to hear you.
okay. Not sure what to do because I cannot turn.
Oh, I think now it's better. I think now it's better.
I think the reason why it was because I just put some paper on my laptop, so it might have that might have been the reason. Okay, so again, I can in principle skip it and just tell you the answer, but then I will just be telling you stories, or I can actually show you the full proof, which I'm going to do. I'm going to show you the full proof, and the price is that we're going to get into a lot of subtle mathematical things, which can be quite confusing, but I'll try to keep the contact with the physics so that you realize this is actually needed for the physics for what we're going to do. So the next chapter is called Vectors and Tensors in Curved Space-Time. No, I'm telling you right now, I'll be initially slightly sloppy with the math, but slightly. I will give you at the end, basically it's a tutorial more than, I'll give you the exact definitions. And the reason why I don't want to give you the exact definitions right now is because I feel that if I give you all the full definitions, and there are plenty of them that I need to give, then there is a good chance I will lose some of you, and I don't want to do that. So I'll give you somewhat sloppy definition so that you see the full picture, you see where I'm heading. And then at the end, I will dedicate a lecture or a tutorial to give you the exact definition so that you'll see that I'm not just cheating you and I'm not just playing hand-waving games. Okay, so basically, what are we going to do now? So I told you that we are, in general relativity, there are two questions that we're going to answer. The first one we basically answered, right? We argued that the trajectory of a free particle, you know, we said that the presence of gravity causes the space-time to be curved rather than flat, Euclidean. And then the first question, which we already addressed, was, okay, so how do we describe the motion of particles in this curved space-time? And we answered it. What is the answer?
Geodesic equation.
The geodesic equation, right? In curved space-time, the motion of particles is described by the geodesic equation. Remember, from the point of view of a test particle, right? The test particle is still in free motion. Nowadays, it's pretty easy to imagine, right? I mean, think of an astronaut, right? The astronaut is subject to the gravitational field of the Earth, but is freely floating in space, right? I mean, it doesn't feel the gravity, but it is subject to the gravity because the astronaut, in the International Space Station, is not just proceeding away, leaving the solar system somewhere, right? It's keep on rotating around the Earth. But from the point of view of the astronaut, again, the astronaut does not feel the gravity of the Earth. It's just freely floating. Right? It's nice pictures. The amazing thing is that, Einstein thought of these things 100 years ago, way before the first man was ever sent to space, which was actually 60 years ago, if you remember. Can't remember. If you've seen, I can't remember either, I'm not that old. If you've seen the news. So the first question we basically answered, right? Inclusion of gravity, curved space-time, and this curvature is what we call the gravitational acceleration, as we just saw, and we just show how to describe that motion of particle in this gravitational field. The second question, which is much more complicated to answer, is how does the presence of a gravitational field act to curve space-time? How does the fact that there is a mass somewhere, or energy, right, because E is equal to mc squared, act to take the space-time and curve it, right? That's basically the next question that we're going to start addressing right now. That's the motivation. The answer to that is going to be given by Einstein's field equation. And it will take us a few more weeks until we derive the full math. And you get the full understanding of what is this Einstein field equation. And then basically the rest of the course we're going to do after deriving it is just find solutions to this equation. Just that you get the feeling. So what we're going to do from here on is to start building up the tools that we need in order to derive Einstein's field equation. And the first thing that we need to understand is how objects that we learn, such as vectors and tensors, how these mathematical quantities can be described in curved space-times, right? Because essentially all the physics that we're going to do is going to be built by these objects, by these vectors. So we better know how to work with these objects, such as vectors and tensors, in this curved space-time. And the mathematical motivation for that is coming from what is known as the principle of general covariance. And I told you that in relativity, there are several principles. So we already encountered one, and now we encountered another one. It's called the principle of general covariance. Principle, that's how you write it, right? Of general covariance. So essentially, we want to understand how the laws of physics can be described in curved spacetimes, in curved spacetime. Understand how to write the laws of physics in curved spacetime. Now, essentially, or philosophically, or the strategy that we're going to follow is the same strategy that we followed when we derived the geodesic equation. Namely, we're going to first consider an equation which describes the laws of physics in flat spacetime, right, without gravity. And we will write this, how do you write a physical equation? Normally you write it with, partial derivatives in this flat metric, right? Remember, velocity is just a partial derivative of location, and acceleration is just a partial derivative of the velocity. Essentially, these are the equations that we'll be interested in. So consider an equation, or we consider an equation that describes the laws of physics in flat space-time. Right. Now, according to the equivalence principle, this equation will hold in the presence of gravity, provided that it is generally covariant. And what I mean by generally covariant is that it preserves its form under the general coordinate transformation when we go from x to x prime. So this equation will hold in the presence of gravity, provided it is generally covariant. Right. Namely, it preserves its form. Under general coordinate transformation. Right, x goes to x prime. This is called the principle of general covariance. These two together, these are known as the principle of general covariance. Which essentially follows directly, give it a second to digest what I just wrote down. This essentially follows directly from the equivalence principle, right? Because if you are in any arbitrary gravitational field, right, and we consider an equation that satisfies both conditions, namely describes the laws of physics in flat space-time, and it is generally covariant, so it preserves its form. So because it preserves its form, it means that if it's true in one coordinate system, it will be true in any other coordinate system because it has the same form of the equation. And from the equivalence principle, we know that at any point in any arbitrarily gravitational field, we can always find a locally inertial coordinate system, right? This is the freely falling elevator. And from this criterion, we know, from the first criterion, then we know that it properly describes the physics in this freely falling system. And so it means that it has to properly describe the physics in any other coordinate system. All right? So do I need to write it down? Maybe I can write it down. So, proof. Consider arbitrary observation field. Right, an equation that satisfies 1 and 2 those conditions. Right, from condition 2 means that it's true in one coordinate system and true all of them. In one system, it is true if true in one system, it is true in any other system. Right. Principle of prevalence of equivalence. There is always, we can always find at every point there is always the possibility to construct a locally inertial system. Like freely falling elevator. And then from one, we know it is true in the system. It properly describes the physics in flat spacetime. On the equation properly describes physics in this system. So it has to describe properly the physics in any system. So it describes properly describes physics in any system. Okay. There is something deep here, really, much deeper than that. The deep thing here is that we want an equation to describe the physics regardless of the coordinates, right? Because the coordinate is something that we put in. Remember, I think we discussed that at the beginning of the course, right? The coordinate is something that every observer puts in for yourself, right? And the physics doesn't care and should not care about the choice of coordinates. So one way of thinking of this principle of general covariance is that it is a consequence of the equivalence principle plus the requirements that the laws of physics be independent of the coordinates. Right? Essentially, the laws of physics should not depend on the coordinates in any way. Right? Don't forget, the coordinate is something that we put for our purpose. Now, because of this principle, this is why I insist on working with vectors and tensors, when you think of that, right? Because I know their transformation laws, right? So I know easily how to transform an equation from one coordinate system to another, which is quite essential here. Because that equations that are made out of vectors and tensors are ones that I can easily imagine, or I can easily find, it's not really easy, but I can find simple ways of making them generally covariant. I can find simple ways of, when I write an equation using vectors and tensors, I can relatively easily find a way of making this equation independent on the coordinate system. All right, that's what we have here. So it's something which is somewhat on the philosophical side, but it's actually quite strong philosophical side. So what we're going to do from here on, actually the rest of this, chapter, so next few lectures would be to generalize what we learned about vectors and tensors which we introduced when we discussed special relativity, right? Flat space-time, to any arbitrary curved space-time, right? Questions? No? Okay, I told you it's a bit on the mathematical side, but I give you the logic, right? There's some deep things here. Okay. So I want to generalize the definition of vectors and tensors to curved space-time. Generalize or generalization of vectors and tensors to curved space-times. Okay. The first thing that I'll give you the bottom line, which is the title. Vectors as directional derivatives. I told you it's going to be somewhat subtle, but it's actually doable. Vectors as directional derivatives. Okay. Now, let's go back to what we spoke about in vectors in special relativity. So remember that when we discuss special relativity, I told you that vectors belong to
the tangent space.
right. They belong to the tangent space at a given point, right? So that means that the tangent space is all vectors that at that single point in space-time. Okay. The price we pay for that, when you think of it, right? If I tell you that all the vectors belong to a given point, so they don't connect between different points, that means that we lost the concept of direction, which you're used to associate with vectors without even thinking too much, right? We have a vector pointing in the x direction and a vector points in the y direction. Now I told you, when we are associating vectors to a given point, we can no longer do that, right? There is no direction. It's only one point there, right? Right. I cannot tell you that a vector in an abstract space points in the x direction because it's just an abstract space. I cannot put the notion of direction. So what we're going to do now, I'm going to retrieve back the notion of direction. We do need this direction to vectors, right? So we argued. Let me emphasize the problem, right? So I argued that vectors belong to the tangent space composed of the set of all vectors at a single point in space-time. Right. And the important wording here is a single point. Right? All the vectors are associated with a single point. So that means all vectors are objects associated with a single point. Which means that we lost a sense of direction. right? You're now floating in space and you're closing your eyes. Which way to go? You don't know. How could you know? Right? All directions look the same. Okay, so now we want to take care of that. So now it's about time that we do some mathematical concepts. Okay, I told you I'm going to do a slightly hand waving. So the first term that I'm going to use is called the manifold. So there is an exact definition, and I told you I'm going to give it to you later on. Right now, a manifold, right? It's an n-dimensional space, which, if you look near each of its points, it looks like a Euclidean space. But globally, so locally it is a Euclidean space, but locally it is not. Okay? So the surface of the Earth is a manifold. Locally it's Euclidean, right? If you look at the floor, it is flat. Globally it is not, right? Right, so, you know, the simple examples that I can give you, right? So we can think of an n-dimensional sphere. So maybe I should lay down. A manifold, it's loosely speaking, it's not a mathematical definition. A manifold, loose definition. A manifold is an n-dimensional space that near each point resembles an n-dimensional Euclidean space. So it's a locally Euclidean but globally not. Right, the space-time. Euclidean space. Okay, yeah, that's enough. So, no, classical example with this n-dimensional sphere, right? So n-dimensional sphere, right? Like the surface of the Earth. That, by the way, is called genus 0. Another example would be a bagel, right? A torus. So torus. Or if you want a bagel, so, you know, have a double torus. These are manifolds. Right, so this is called genus 0, by the way. How is this called?
1.
Genus 1. It has one hole in it, right? It's a bagel with one hole. It's called genus 2.
What about a Mobius strip?
Forget about Mobius strip now. Focus on what I'm saying. Don't overcomplicate things.
Sorry.
Now, I'll ask you that in person in the homework. This, for example, is not a manifold. It has to have the same dimensions, right? A porcupine is not a manifold, right? It cannot have sharp edges. Okay, this is not a manifold. And near each of its points, it has to have, you know, it's the same n-dimensional Euclidean space. So if you go, you know, if you look at magnifying glass, you know, you look closer and closer and closer to a point, it will get Euclidean. Okay, so a porcupine, so you cannot have like sharp edges, needles, right? So, you know, mathematicians can think of all sorts of crazy spaces, right? This is a space, right? This is not a manifold, okay? And you realize why. So for me as a physicist, right, for us as physicists, right, the manifold is something which is well behaved, okay? If you look close enough, it looks Euclidean. How close? Depends, right? Okay, that's clear? Good. Okay, this actually is also Riemann surfaces. This is a two-dimensional sphere, of course, right? But you know, you can think of it obviously in any dimension, right? There's no limit to the dimension. The next thing we're going to do is we're going to put now structures on the manifold. You have to be careful because vectors and tensors are external structures to the manifold. So you don't really need them in some basic sense. Practically, okay, we'll get there when it comes. Let's talk now about vectors and tensors in curved spaces, or just vectors, forget about tensors for now. Vectors in curved spaces. So the next thing we want to do is we want to put vectors on the manifold. Now, we already know that vectors belong to the tangent space, right? The problem is I haven't, on a curved manifold, I really haven't yet defined what is a tangent space. I want to construct a tangent space to a point P on a manifold, which is general. But here is the crucial thing. I only want to use things which are intrinsic to the manifold. I don't want to look from the outside. All right. Again, we know that the Earth is round because you can say, okay, I can send an astronaut and he will take a picture of the Earth and you'll see that it's round. But that is cheating because that's taking the astronaut outside of the Earth. I want to prove that the Earth is round from within the Earth. I'm an ant now. I'm a very wise ant that I cannot leave the surface of the Earth, and I still want to find a clever way of you know, defining things on the surface of the Earth without leaving it. Okay. So similarly, right now, and I'll show you that the ant, if it's clever enough, would be able to show that the Earth is round without leaving the surface of the Earth. We don't need to leave the surface of the Earth. We don't need to look from the outside. We're not there yet. What I want to do now is something which is some steps before that. I want to construct a tangent space to some point P on the manifold, and I want to do it using only things that are intrinsic to the manifold. Manifold, by the way, obviously I'm going to call it M. A manifold. And I'm going to call my manifold M. So I want to construct, or we want to construct the tangent space at a point P on the manifold M. The manifold, of course, is going to be the space-time, right? So this is going to be the point P in the curved space-time. Right? But here's the catch, using only things that are intrinsic to M. Okay. So again, I'm going to get you through that. It's a little bit of mathematical subtlety. So you do have to think a little bit about that. And the real reason why I'm doing that is because I want to show you that I'm not tricking you and I'm giving you the right pieces here. So how do we do that, right? So, we know that the tangent space is made of objects that are, tangent vectors to curves. Right? So we can draw curves on a manifold, and then the walls pass through some point P. And then we can, what we did previously was, without really thinking too much, we just say, okay, we define a tangent space as simply the space of all the tangent vectors to the curve at that point P, right? So I have a manifold.
Sub the buzz. Stop.
Sorry. Sorry, can you hear me now? So I have my manifold here. I put a point P on the manifold, right? And now I can construct some curves. So again, there is an ant that walks on that manifold, right? So I have an ant here, and the ant just walks on the manifold like that, right? So the path that the ant takes just crosses a curve. And I can specify the curve by some parameter lambda, right? And there can be a second ant that walks on that manifold, and it also crosses at a certain point, the same point P. Right, and I can specify that. Did I choose a new number? No, I can choose new. Right, and I want to say, okay, so I can specify a vector which is tangent to that curve. Right, so I can say, okay, I have a vector here, which will be something like that. Right, so a vector here, and I can have a vector here, which will be something like that. Right, at that point P. Now, of course, I did that last time when we spoke of free spaces, of flat spaces, but I'm not doing it right now because I haven't really defined what is the exact meaning of a tangent vector to a curve when we're speaking about curves on curved spaces or in general manifolds, right? Yeah, so if I were to do that, I would simply have to use the, I could say it's an element of the tangent space, but that's what I want to do. I want to define what is the tangent space. Okay, so the next step would be to take that and to try to erect some coordinate system on that. So how do we do that? So we take that. How do I take that? I'm sure I have a way of, there's a clever way. Maybe it's this one. No, not this one. I have something like that. Copy. I might put it here, I might do a paste. Ah, I love this technology. Right, so the next thing I'm going to do, I'm going to put some coordinate system, right? So I'm going to put some coordinate system, which around this point P, which I can define it in the vicinity of the point P because I told you that the point P, locally the manifold looks Euclidean, and in Euclidean space I know what to do. Right, so in the vicinity of the point P, I can put some coordinate system. Right, this is my coordinate system, which I'm free to erect in the local of the point P. Again, because by the definition of the manifold, around every point it resembles a Euclidean space. And that means that any curve that goes through P, it is defined essentially an element in Rn, right? By the derivative, right? By dx mu over d lambda. So that was the wrong choice of coordinate here. Let's call this C. Right? So if I have if my coordinates, I call them x mu, right? Then the curve here, right, it's just going to give me a set of coordinates, a set of numbers, which are dx mu over d lambda. Right? How the coordinates that I put change along the path that I take, lambda in this case. right? At that point P, where lambda, of course, is the parameter that essentially specifies the curve that I'm taking, right? So I can think of it as a set of n numbers, right? So this belongs to Rn. Right? Okay. This is not bad because I'm using only things that are legal. The problem is that this is still not general enough for my purposes because this depends on the coordinates that I choose, right? This x mu, which were done arbitrarily, right? You could choose your own coordinates and it will be different. And I want to get something which would specify this curve essentially, right, on the vector in a coordinate independent way, right? Something which does not require any coordinates. So the way to do is the following. We're nearly there. We want to have, okay, okay, you're all with me? Do I need to write it down? Maybe I should write it down, right? We can always erect coordinates in the vicinity of point P, and then a curve will be a curve lambda curve lambda will define an element in Rn, which is dx mu over d lambda, and is the dimension of space, right? But this is coordinate dependent. We want something that has nothing to do with coordinates. So what coordinate dependent, and now a coordinate independent way. So let's take again this good. Is it larger? No, a little bit larger. 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 Yeah. A little bit larger. Could we press up? Oh, it's larger. Then I can do this one. No. Why are you doing that? Finally, good. So here's the way to do it. Okay, so we define the space of all smooth functions on the manifold, namely mapping from F from M to R. So this is the manifold M. We look at the function F, which is really a mapping from M to R. And F, capital F, would be the space of all these functions. Space of all functions. F. And F is just a mapping from M to R, right? And each curve that we have really defines an operator on this space, right? This is really the directional derivative. So each curve takes F. So again, F is a mapping. So for every point in M, it gives me some value in R, right? And right, so this will be like a point here. This is P. This will be f of P is a value in R, right? And the curve defines a directional derivative mapping. So from F, this curve here will define a mapping from F to df d lambda at P. So the curve is really defining an operation at the point P, which is done in a coordinate independent way. Let's see if I give the right explanation here. Right. Okay. Now the claim is that the tangent space TP is identified with the space of directional derivative operators along all the curves through P. So TP can be identified as the space of all directional derivative operators along curves through P. Okay, that's been a bit abstract. What do I do again? I'm looking at mappings from M to R. So there is a set of functions, right? Infinite number of functions. For every point in P, I can get a function which will map it to R. It's somewhat similar to the coordinates, right? Essentially, this is what the coordinates do, right? For every point on the manifold M, it gives me a set of numbers, right? But done in a more general way. And when I go along the curve, right, the directional derivative along the curve, really, I can view it as operator in this space. Namely, I'm taking the function f and I turn it into another function, which is df d lambda. Why is that true to identify that with the tangent space TP? Well, first it is a vector space. Proof. One, it is a vector space, and two, that it is the vector space that we're interested in. And two, it is the vector space we want. Which means, okay, it has the same dimensionality of M. Okay. So, what do I mean by that? So how do I know that it is a vector space? That's quite easy, right? So I specify for each curve, essentially what I did, I specified directional derivative. So I had the curve lambda, and now I specify directional derivative d over d lambda. I had a curve, change the name, I want to call it sigma. Then this specifies an operator d over d sigma, right? So the first claim I said, this is a vector space, right? So if I have two operators, which would be d over d lambda and d over d sigma, this would be two operators, right? which represent derivatives along these two curves that both go through P. Right, so I can think of these curves as you know, x mu of lambda and x mu of sigma. Right. So obviously I can add these curves. I can add and multiply by real numbers, and I can get a new operator. So I can always get a d over d lambda plus b d over d sigma is a new operator. So this is a vector space. But this is the vector space. Okay, sorry. We still need to check out that this vector space closes, namely that this is also a derivative operator, which is clearly it is, just by looking at it. But you know, the standard way is to look at the derivative operator that works on any functions, and that it has to obey the Leibniz rule. So this vector space closes. Right. Namely, it acts linearly on functions and obeys the product rule of functions. So the new operator is obviously linear, which means that a d over d lambda plus b d over d sigma operating on two functions, f times g, is exactly what you get normally, right? A f dg over d lambda plus a g df over d lambda plus bf dg over d sigma plus bg df over d sigma, which is just a df over d lambda plus b df over d sigma g plus a dg over d lambda plus b dg over d sigma f. Where f and g, again, I treat them as two functions, general functions from the manifold M to R. So they belong essentially to this space F, capital F. The product rule is satisfied, so that means that this new operator is indeed a derivative operator. So the set of directional derivatives is indeed a vector space. That shouldn't be of any surprise to you. Only that now the way we worked on it, right? We looked at directional derivatives over curves along any arbitrary manifold. Okay. And then the second question is, can we identify this vector space as the tangent space, right? So of course, yes, right? And one way is, of course, to find a basis for this space. And again, if I'm looking at general coordinates, there's some coordinate x mu, then there is obviously n directional derivatives on P again. So if I look again in the vicinity of this point P, right, then I have, I can set this point P. I can set coordinates on this point P. Right, so let's say this is x1 and this is x2. Right, and so again, the directional derivative would be this one. Just take the derivative along 1. This will be d1. And this will take the derivative along x2, keeping the coordinate 1 fixed. So this will be d2. The natural sets of directional derivatives will be the partial derivatives d mu at p. So the natural basis is a set of n partial derivatives d mu at p, right? And that define the directional derivatives along curves, which is in the direction of the coordinates that we chose, and keeping all the other coordinates constant. Now, the argument, of course, is that the set of these, I'm sorry that I'm taking a few minutes off, just I need to finish this argument. The set of all these partial derivatives, partial derivative operators, d mu, this form a basis for the tangent space TP. What's your basis? So the set of n partial derivative d mu is basis of tangent space TP. So, of course, in order to show that this is a basis, the simplest way that what we need to do is to show that any directional derivative can be decomposed into the sum of real numbers times the partial derivatives. But of course, this is just the what we've seen as the expression of the components of a vector. Right? So again, if we have an n-dimensional manifold and we have a curve, n-dimensional manifold, I have a point P, and I have a curve, gamma. Now note that I'm looking at the curve as a mapping from R to M, right? So if this is my manifold M, right, this is gamma equal to 1, 2, 3, 4. So every value of gamma, right, gives me some point on the manifold. So I can think as the curve gamma as some mapping from R to M. Okay, and any function f that takes from M to R. Right? So if gamma is the curve, sorry, I can specify it, I should have the lambda here, so lambda equal to 1, lambda 2, lambda 3. Right? So if lambda is the parameter along the curve, right, then we can expand the vector or the operator d over d lambda in terms of the partial derivative. So expand the operator d over d lambda. Right. So d over d lambda of the function f, right, what is that? It's just the limit where epsilon goes to 0 of the function f at the point x mu of lambda plus epsilon, right, minus f at x mu of lambda divided by epsilon. But this is nothing more than dx mu over d lambda times d mu f. That's true for any function f.
Asaf?
Yes.
What did you write in the first function? The derivative x mu lambda plus
Epsilon. just going along this curve, right? Again, the logic goes as follows. Gamma is a curve, right? Lambda just specifies the parameter along the curve. F is a general function. I don't want to specify coordinates because I don't want to work with specific coordinates. So in the vicinity of the point P, right, it looks Euclidean. So I can set a function F, right, which takes a point on the manifold and transfers into R. If you get confused, basically I number the points here, right? Like I'm putting coordinates, but I want to do it in a completely general way. So think of it as a coordinate, right? I have a space, right? What does it mean that I put coordinates on a space, right? So I tell you, this is my space, right? I say this point is x equal to 1, y equal to 2. So I map this point of space here. I map it into R2. I gave it two numbers which fully specify this point here. That's the meaning of giving coordinates to a point, right? I actually made a map from the space into R2. Okay. What I'm doing is I'm taking this to another level of abstraction. I mean, it's not another level, sorry, it's the same abstraction. I'm just doing it in the abstract way. I'm mapping every point here to R. Okay, I didn't want to do it with using the coordinates because if I were doing it using coordinates, I would have to specify more coordinates first. The reason why I do it like that is because I don't want to specify more coordinates. But as I showed you, I don't need to. Now, when I do it, I can look at this curve here, right, as an operator, because essentially it takes the function from here and just shifts it along this curve. So I can think of it as taking it to a different function, right? But this curve here, right, is just a partial derivative. So what the end result of all this long story, right? So just we should finish with what I just did here. So I did it with d over the lambda of f. F is an arbitrary function. It's just dx mu over the lambda d over the mu of f. Since f is an arbitrary function, that means that d over the lambda, I can write it as dx mu over the lambda d mu, right? Or d over dx mu, right? And the reason why I wanted to do that is because I wanted to show you that d mu or d over dx mu is a good basis for the vector space of directional derivatives. D mu is a good basis for the space of directional derivatives. Okay, I thought it's going to get a little bit confusing. I'm doing here something which is very, at the end of the day, I want to do one thing. I want to specify a vector with the directional derivative along the curve. That's what I want to do. I'm going to argue that my concept of a vector is at the point P, right, is identical to directional derivatives of relevant curve at that point P, right? Now, obviously, this vector that we just put in, d over d lambda, is exactly this tangent vector to the curve, lambda. Right? So it's just some sort of restatement of what we really did, of what we did in special relativity. Actually, the only difference between what we did in special relativity and what we're doing now is that in special relativity, we had a flat space-time, and now we work with arbitrary manifold, which is not necessarily flat. So in special relativity, we use the notation of E mu, right, as a basis vector, and now we're using d mu as a specific basis. Okay, I could have skipped all this part, but then one of you might have caught the subtle point and say, wait, how can you do that? So, bottom line, what I really did here, I was interested in defining vectors on the curved space-time. I could not specify directly as a tangent vector space because I don't know what is a tangent vector space before I specify what is a vector, right? And I wanted to specify the vector in a way which is completely inherent to the manifold and is independent on the specific choice of coordinates. So the way I did it, I said, okay, what is inherent to the manifold? The only thing that is inherent to the manifold is my ability to walk over it, right? So I can put some curves, right? I can specify some curves. Think of an ant that walks on a ball, right? The trajectory specifies a curve. This is something which is inherent. I don't need to leave the manifold for that. Now, each of these curves, I can essentially, I'm going to specify a tangent vector to this curve, right? Now, if I try to specify the tangent vector to the curve in a straightforward way, I will get stuck. Why? Because in order to get it in a straightforward way, I have to specify a set of coordinates. And then I can obviously specify a tangent vector to the curve as the, the change of these coordinates along the curve, right? Dx mu over d lambda along the curve lambda, which is fine. I can do that. But the reason I don't want to do that is because if I do that, that is dependent on the coordinates that I'm specifying. So I want to do it in a way which is coordinate independent. So the way I choose to do it, I said, okay, rather than simply look at coordinate, I can look at the general abstract space of functions from M to R. Now a coordinate is a function from M to R when you think of it. Again, when I say a coordinate in space, what I really do, right? I assign numbers to a point in that space, right? I simply assign numbers. So I can think that coordinate is also a function from the manifold to R or to Rn, right? So here I'm saying, okay, so let's look generally at functions from the manifold M to R, right? And again, in that case, these curves act as an operator, namely it takes one function and turns it into another function. And the function that it takes it to would be the f over d lambda. So I can think of d over d lambda as an element of this, for all these operators, d over d lambda, these would be the elements of the vector space. So the bottom line of what I do here is that I associate vectors with directional derivatives along curves. This is the important thing to remember after all this math. If you got messed up with things here, right? And this is something which I can always do on any arbitrary curved manifold, provided it is well behaved, as you remember, right? It's not a porcupine; it doesn't have any spikes. Okay. It's okay. Relax. It's there. I'll repeat that and resume and proceed with that along this direction on Sunday. Okay. I've already taken too much of your time. So see you all on Sunday.
Thank you very much.
Proceed with that. To the stop sharing and let's stop recording.